Hello and welcome back to Junction Embedded. I am Mohammed Hussain, and again I am very much thankful to all of you who have subscribed me, who are sharing my videos. Please keep doing like that. I will also continue my work here. So I have listed some topics here which I will try to cover today. In our last session, I discussed about the boot up sequence. So there is a boot flash which holds the internal state machine of checking the validity of the code inside the ROM or RAM. Next we have ROM, or I will call as code flash also. Then we have RAM, and then we have peripheral mapping. So, and this all is in a microcontroller or a microcontroller, and inside a microcontroller or inside a processor you have a program counter registers. So initially at startup, when you just power up a microcontroller, everything is 00 or everything can be loaded with FF. It depends again on the architecture of type of microcontroller what you use. So to make it simple, let's assume that it's using a 16-bit address and everything at startup is 00, and this memory also starts at 0000. So the program counter is nothing but it loads the address. It has the address of the next instruction what is to be executed. So as of now, program counter is pointing to boot flash memory at the startup. That's how your the internal boot machine is called, and it is executed to check the validity of the code in the ROM and RAM. Suppose if some piece of code exists in the ROM area, it will go to that particular location, and that location will be again loaded into, let's say this the base address of this code flash is some 500 location. So the program counter will be loaded at 500 location, and then the program counter will be pointing to the code flash and the execution will start. Let's expand this area. Okay, so it's executing, it has some starting address 500 and it goes up till, let's say, 1000 area or anything. This addresses I will show practically how they are mapped in the data sheet. But for example, let's assume this starts at 500 and goes till 1000, and this is the base address of the code flash area. So here most of the times you will find an interrupt vector table here, or the reset, at least the reset vector is available here. I will call it as, let's say, reset vector again, which has the address of the reset ISR. So there are a lot of things which happen here again. And there is one more startup code here. So this all is actually right now out of the scope of today's topic, because this startup includes the PLL initialization, it has the interrupt vector table initialization, the memory initialization, the BSS section and everything. So it has a lot of things which I have not gone through yet. So this will be definitely covered at later stage. It's a kind of reverse way of learning, that the basic things will come at the later stage, but I don't have any other option. After the startup code, your main code will be here, your main function, and if you have any other functions in your code, all the functions will have some memory space in this code flash only. So this is not the function stack I'm talking about. This is the code area, the text area, which has the instructions, the low level binary instructions, the opcodes, and after the boot flash gives the control to this code flash, all your main code and everything will be executed from this memory. So that's how the code execution starts, from the boot flash, from the base address, or from any other address at which boot flash is located. As I told you already, that I have taken an example of 00, but not necessarily that this boot flash is always located at 00 location. It can be all ones also, or it can have some in between range. But irrespective of the memory location, the boot flash will be the first thing which will be called by the microcontroller, and which will be whose address will be stored in the program counter. So this will be the first thing which will be executed, and this part you can check in my first video, that where the it will check for the validity of RAM and ROM, or maybe some ISP handler also. Then it will go to the startup code. Then the startup code calls your main function, and inside the main you can write your own code from today we are going to discuss about the GPIO. So we will write our GPIO code here in the main function. We will be setting high and low a particular pin. What I mean by setting high and low is again the peripheral and GPIO hands-on. Let me move to that topic. As you might be knowing that there are so many peripherals inside a microcontroller, and in my first video also I discussed about a few. So let's talk something about the GPIO in detail. GPIO is a peripheral which provides us the means to set or reset a particular microcontroller pin. So if this is a pin of a microcontroller, we can set it as high or low. We can high being, let's say, 5 volts, or 0 volts, logic 1, and this will be logic 0. So we can set it or reset it by the means of GPIO registers. GPIO is again divided in some ports. So let's say there's a port A and there's a port B. For again, port A can have many pins and B can have many pins. Let's say there are 8 pins in port B and 8 pins in port A. Now, to access each pin, there will be some registers. There will be some registers which will set the value of that pin. We will call that registers as, let's say, port A register. Okay, similarly we'll have some register in port B. Let's assume that this is an 8-bit register. This is an 8-bit register, and each bit represents one pin status. So if you want to set the 0th pin, this is port A0 pin. If you want to set this pin as high, you can just set it set a 1 in the 0th bit. Okay, this is being the 0 bit first and second. If you want to set this port A.1 pin as high, you can set as 1 here, or if you want to reset the pin, you can set as 0. You can clear that bit particularly. So that's how you will control the output pin. But GPIO is not only about giving the output or providing the output. GPIO means the general purpose input output. So there should be some means of taking an input also. So that's how the direction register is used. With every port there will be a direction register, or with every pin there will be a direction register associated, which will tell whether this bit is going to be an input or output. By default, so many controller uses 0 as input or 1 as output. So if this bit is 0, the port A.0 pin will be as input, or if this bit is 1, this particular pin will be treated as an output. Then only you can set some value here, otherwise this port register value does not have any significance. Again, this direction register will come into picture when this particular pin serves as a GPIO. What do I mean by that is, GPIO is not the only peripheral which this microcontroller has. There are so many peripherals existing at the same time. Let me draw them. So as you can see here, this pin can be treated as a GPIO pin or SPI or UART, and this is nothing but a pin multiplexing, that at single pin you can have many outputs, but one at a time. And this selection, that which peripheral has to be chosen, is again a register, which is pin cell register, pin select, that what functionality you want to select on that particular pin. Because there is a possibility of 4 peripherals at one pin, the pin select register associates 2 bits with each pin. So this is being, let's say, for the pin number, this one we assume that port A0. So port A0 has 2 bits. So if these 2 bits are 0 0, this will be connected here. This pin is going to be a GPIO. If you select this as 1, it will be the first functionality and it will be connected to the SPI. But if you select as 1 0, the value being 2, this will be connected to the UART pin. So that's how the selection logic works as a multiplexer. This will be nothing but a multiplexer selection line, and each pin will be having 2 bits here. Second thing is you have to change the direction. You have to make it as an input or output. So for that you will use the IO DIR register. I was telling about the some DIR register, like in Atmel microcontroller you will have data direction register, which is DDR. In the LPC controllers, what I am going to use today, LPC2138 has IO DIR register. Then the third thing is IO set register, and another register is IO clear register. So as I told that the pin can be made as an input or output using this register. So here you will select input or output. Here in these 2 registers you will set that pin as particular as high logic or low logic. If you want that pin to be high state, you will set this pin, or if you want to clear that pin, you will set this register. By default everything is 0 0 at startup. When the system boots up, when the system jumps to the boot flash, and from the boot flash the code is loaded, before coming to your main, all the registers are set to 0 0. What does it mean? It means that by default the pin selection register completely is 0 0. That means GPIO is selected. By default the IO DIR register is also 0 0. That means everything is input, and everything is 0 0 means all the pin state is also 0. Now let us go to my laptop and check this practically. And before we download the code to the development board and see the LED glowing, I'll tell you how the LED is connected in my board. LED is nothing but a light emitting diode which emits light when it is in the forward bias condition. What I mean by forward bias is this LED has 2 terminals, P and N. When the voltage of this P is greater than the voltage of this N terminal, then you will have light. And when this condition is not met, then there will be no light. So we will be connecting the P terminal of this LED to our microcontroller, one of the input output. So let's say port 0.0 we are connecting here, and the negative terminal is always grounded. We will not connect this terminal directly to the LED. We will be having some current limiting resistor so that the current what flows into the LED can be limited by this resistor. So that's how the LED is connected in my board. And if you set this pin as high means plus 5 volts. So there is a difference between this PN junction layer and the diode is forward bias. The P part is 5 volts and the N part is 0 volt. It will emit the light. But if you clear this pin, if you clear this GPIO pin which will be having 0 volts and 0 volt matches with 0 volts, there is no light in this condition. So we are doing this in our software. We are taking care of making this pin as high and low repetitively at the rate of 500 milliseconds. Let's see it practically. And here's my development board, which has microcontroller which is LPC2138 on the top, and then you have so many pinouts, probably for GPIO or SPI or so many peripherals. Then you have some UART port here, which is used for the programming. This is the programming circuitry. This is also nothing but a USB to serial converter, because in laptops we do not have the serial port provided. We have only USB port, so one circuitry is needed which converts the USB to serial, and here you will get the serial data, and the serial data will be downloaded to this microprocessor. And connecting this development board to your laptop is very easy. Here you have a USB cable, you can just plug into your USB port. So here's my laptop screen, and first of all I'll show you the device manager. So as of now I have not connected the device to the system, to the laptop. So there are no USB devices with communication category. Once I connect the device, so the list refreshes automatically, and this device is detected as a COM port, as a COM5. In your PC, in your laptop, it will be a different port, or it can be the same also. Uh, and this port is used for downloading the code to the microcontroller serially. And the ID, what I'm going to use is again a free source programmer's notepad, which is available on the web, and you can download it from its website. Here you can create a new project, or you can open some existing project. Uh, First, let me go to my directory where I have some project already existing, in which I have written one C file. I have just made a template for you. I have not written any code still, but it just has a template. So this project only we will be using in this way. I'll open this project here. Okay, so I have this main file, I have this header file and a make file. Before I start writing the code, let's open the datasheet of this microcontroller LPC2138. Here's a user manual. So the user manual is for these many controllers from 2131 to 2138, and as you can see there are a lot of peripherals here: Gpio, UART, SPI, timer, PWM. So many peripherals are listed here, and there's a memory map. Okay, let's see the memory map first of all. So here's the address 00. They are using a 32-bit address bus, so all the addresses are 32-bit aligned. And the first address, the base address, is 00, from where the non-volatile memory, which means your code flash memory, the ROM, starts, and it goes up till some value, depends on the device what you are using. We are using LPC2138, so the memory size is 512 KB. Then there is some reserved area here, and from 4000 it starts the RAM, and again RAM has again so many sizes depending on the availability of the device. If you have LPC2138, then you have 32 KB of RAM. If you are using 2131, then it's only 8 kilobytes of RAM. As you move upwards, again some reserved area, and after that the boot block comes. What I was talking about, the boot flash, where the startup code is written, where the hardware bootloader resides, and the internal state machine to check for the RAM and ROM. Everything is here. Then you have again some reserved area, and then you have peripheral memory. Uh, Peripheral memory mainly contains the registers, a lot of registers, so many registers to set, reset, or configure your peripheral. So let's see what are the addresses of the GPIO block. And if you remember, we are going to use four main registers, which is pin select register that you can find in this pin connect block, and there are three pin select registers to select different port pins. So pin cell 0, register can select from port 0.0 means the 0th pin of port 0 to the 15th pin of port 0. Then you have pin cell 1 register which can select again from port 016 to port 032 or 31st pin. Pin select register as of now will not be using because the reset value of all the pin select registers is 00. You can read here that pin select 012, the reset value of all the registers are 00. That means everything is by default GPIO. So we will not be using this register today, at least for GPIO. Next you have the GPIO peripheral, and in the GPIO peripheral you can actually read the data sheet that how many ports are available and how many pins are dedicated for each port, like that. Then you can click on register description to see how many registers are available. As you can see here, IO set, IO dir, IO clear, I already told you. Set and clear are used for the output. Direction is to decide that it's an input or output, and pin is to read the input. If we are going to use IO set register, we can take this value IO set register and we can just use this address using a dereference uh, star, and we can give some value like this. So this way you can give some value to that port, but it will be very difficult for developers, for us to remember the register of each port. And this is only GPIO. When tomorrow we talk about SPI, UR, there will be a lot of registers we'll be handling with. So this is not the correct way to do it, and that is why we have this LPC2138.h file here. In this file you will have a lot of addresses and the definitions. So here you will define actually the macros or the type definitions of each register, and then you can use these definitions in your code to point that memory. So if you remember the address of that GPIO block, it was E0028,000, and it is E0028,000. So this is the first register IO pin, and here also IO pin 0, then IO set 0, dir 0 is there. So you want to use IO set 0, you have to just copy this from the header file, and instead of this statement you can write the macro. So as I told in the theory part, that you have to use the pin select register for the selection of the GPIO or the peripheral, but no need to select specifically because by default everything is GPIO. So the pin select we can skip as of now. Then you have to select the direction. So for that I'll be using IODIR1. Actually in my development board the LEDs are connected to the port 1. That's why I'll be using IODIR1 and IO set 1 and clear 1. So in the IODIR1 or in my port 1, the LEDs are located at the LEDs are connected from pin number 16 to pin number 23. So there are 8 LEDs connected from 16 to 23, and that's how I am selecting this direction. I don't care about these ones now, these being the inputs. I'm not using them, but I'll be using this pin number 16 to 23 as output, so I have made them as 1. You can use a decimal value, you can use a binary value, or anything which you are comfortable with. I am comfortable with using hex values, so I'll always write in hex. Once the direction is selected, you can always set that particular value. So if you are setting all the pins as 1, you can say FF, or if you want to set just one pin, maybe the 0th or the 16th pin, you can just say a 1 here. This location is nothing but the 16th bit, which correspond to the 16th pin. Similarly, you can write the clearing code. So if I execute this code now, it will be executed within microseconds and you will not see anything, because it will be set and again reset within some microseconds, which will not be visible to you. So you can put some delay here. Okay, and what we can do is we can put a while loop. In embedded systems, in all the embedded system, it's always a while loop. That means you have to the board is supposed to do this repetitively. It should not exit this main code. There are some again scenarios, like if you are going to sleep, if you are going to restart the system, you may exit this loop, but in general, once the system start, it should not leave this loop. Now the delay part is left. I have some function already defined, timer 1 delay, and I can give some maybe let's say 500 millisecond first of all delay. This function is supposed to introduce a delay of these many milliseconds what you pass here, and this timer will be covered in the next video, where I'll show you how to so to run this delay properly, I have to call one more function, which is init timer, and those will be covered in the next video. But as of now, you can assume that this is a library function which will introduce a delay of 500 milliseconds. Now let us compile this code and see how the code works. To compile this, you can click on tools and you can say make all. So if everything is fine, you will see that linking and everything uh, goes smoothly here. The files are generated. If you can go back to the folder where we are using, so you can see ALF file and the hex file and all other like map files are generated here. The object file is also here. So you compiled your first code successfully. So before seeing it on the board, now let's download this code, and you can download using this make program. Once you click this one, it will open the serial port, the COM5 port, and it will transfer the data over the USB, and that small device what is connected in between between the USB and the development board converts the USB data to the serial thing. So once you click on this one, so here you can see the COM5 is opened with 9600 baud rate, and uh, this is the image size like 3 KB, and this is all ISP related thing, like it will first synchronize with your microcontroller and all. Then it is reading the part ID, which it has got as LPC2138, and it started the downloading after reading the part ID, and then it says download is finished. Now let's see that whether our code is running fine or not. So you can see now that the LED is blinking at the rate what we have defined, and We have used only one GPIO pin, so only one LED is blinking, but you can play with it now. You can use all the LEDs to glow, or you can increase or decrease the timing of this blinking.
So what we can do now is we can select all the LEDs to glow, and we can turn them off after 100 milliseconds. So this way we will check it. Now let's compile this code and let's download and see.
So you can see now that all LEDs are blinking at the rate of 100 milliseconds, and it looks like a disco light. You can play with it. You can play with the delay, the number of the lights, or anything you want. You can make your own glowing style, or you can try something like that. It looks like an insect moving back and forth, but it goes to this point and immediately it comes back here. So it's like this, but you can try with your own logic, with your own code, and this being your assignment now. It should not immediately come back to the zeroth LED. It should again traverse back the path from which it has come to this point. And if you want to know that how I have used timer logic to generate a delay of 100 millisecond or any other time slot, you can comment here in this video, or you can wait for the next video, because the next video is going to be on the timer peripheral, where I will explain how the delays are generated using timers. And if you want to subscribe, please click on this button, and stay tuned to my channel for upcoming videos. Thanks for watching this video. See you next time. Bye bye.